So yeah, thank you all for coming to Paleo Perks today. Today we'll be hearing from Rodrigo Martinez-Abarca, who is based at the Institute for Applied Geophysics in Germany. And he'll be talking about climate and environmental variability in the eastern equatorial Atlantic and the northern tropical Americas, from orbital cycles to human activity. So a bit about the format of today's seminar before we get going. We'll start off right now with some welcome and announcements, and then we'll move into the talk itself, which should last about 30 minutes, give or take, but no stress, Rodrigo, if you go a little long or a little short. After that, we'll have a moderated Q&A, and during that time, during the question and answer, you can send your questions to the questions at Paleo Perks host via chat, who today is Aharna. After that, Rodrigo has agreed to stick around for tea time, which is a more informal, casual way to get to know each other. And if you have any extra questions that you don't want to ask during the Q&A, or if you just want to chat and get to know our speaker a bit better, tea time is a great time to do that. So a little bit of Paleo Perks housekeeping. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself during the duration of the talk. And if you happen to find yourself unmuted at any point, please make sure to mute yourself. You can ask questions again by chatting to the questions at Paleo Perks host, or alternatively by using the raise hand function during the Q&A time. Additionally, any technical issues should go to the questions at Paleo Perks host. We have closed captions built into Zoom. You can use the CC button to show or to hide them. Additionally, you can nominate an early career researcher here if you think they'd be a good match for the seminar series, and that link will be shared shortly in the chat. Additionally, we are always eager to have weekly feedback from you all, which just collects some basic demographic information. It's completely anonymous, it's completely optional, but it is encouraged, and it really helps us shape the seminar series to best serve the paleo community. And you can also find that link in the chat window. So finally, moving on to our speaker. Today we'll be hearing from Rodrigo Martinez-Abarca, who studied both the bachelor's and his master's at the National Autonomous University of Mexico, then went on to do a PhD at TU Braunschweig in Germany, and is currently a postdoc at the Institute for Applied Geophysics, also in Germany. So with that, Rodrigo, I will hand it over to you. And yeah, best of luck.
Thank you so much for the introduction. Thank you so much for inviting me, and thank you so much to everyone for being here this afternoon in Germany, morning, Latin America, or wherever you are. And I'm super happy to share with you. Well, first of all, you can see my screen. I hope so. Yes.
Yeah.
So thank you so much for being here, and I'm gonna talk about two projects that I'm working right now. One is part of my postdoctoral project, and the second one is the last part of my PhD that I finished like already 1 year and a half ago. But I'm still working on the data, so I'm happy to show you the upcoming publication that is gonna be possible in a couple of weeks, hopefully. And yeah, first of all, I would like to tell you that this presentation, even I'm here standing in front of you, this is not only about myself. This is a long collaboration work with several colleagues in Germany and around the world. Are some of them, and also a lot of technicians, students who have been involved in the International Continental Scientific Drilling Program, and also in the Oceanic Drilling Program and ECORD and etc. So I'm really happy to show this amount of work. This presentation will be divided in three parts. Starting with, because, well, maybe some of us have knowledge about the quaternary climate, but some of you maybe doesn't. So I'm gonna talk about a bit about the quaternary climate, what we know about that, the general concepts, and also then I will go to the second part of the presentation that is about the last 1.3 million years recorded in a marine record in West Africa. To talk about the monsoon, the dynamics in the monsoon system, and also something called high precessional cycle that I'm going to explain to you that later, and how these cyclicities could modify the monsoon system through this time. And finally, in the last part of the presentation, I will go to one of the oldest lacustrine records in Central America, in the northern tropical Americas, called Lake Perenitza, and to talk about changes in the temperature that we are reconstructing using some biomarkers, and from the last glacial maximum, the last 20,000 years, to the Holocene, through the Holocene until the most recent times, and talk about the human activity in the area as well, briefly. So I'm gonna talk first about the quaternary climate very quickly, actually. Um, this table is the chronostratigraphic table, and you will see that the last 2.5 million years of the history of the planet comprises the quaternary, and this is only 0.05% of the Earth's history, but um, a lot of things have occurred during this period of time, and including several changes in the climate, and also and these ones produce a lot of changes in the ecosystems, and yes, it's an important period actually. Even it's only a small percentage of the Earth history have produced several changes in the climate. And how we know that? Well, basically using sediments, these unconsolidated materials that are deposited, well, in different environments, but I'm going to talk about the sediments that are deposited on the bottom of the water bodies, and especially two lakes, the lacustrine sediments and the ocean, the marine sediment. These photos that I'm showing you here are cores really in 1993 in the IODP site 663, and you can see two changes in the colors. So darkers are and white sediment. The dark is related with interglacial periods or warm periods that I'm gonna tell you explain to you in the next slide. And this white color that you can see is what we call glacial periods. So when the Earth was colder than today. This is what we can observe in this stack curve made with different marine records wait a second, through the marine basins. This is the delta of the 18 delta oxygen 18 from foraminifera, benthic foraminifera in different records, and basically what we can observe is that low values of the isotope represent the interglacials of the warm periods of the last 1.2 million years, and higher values indicate glacial periods or the cold phases of the history of the planet during the last 1.2 million years. And what we can observe is two different kind of worlds that we call it. So we have this 40,000 years world that is when the obliquity of the planet, so this orbital cycle was one of the responsibles of the climate change in the planet. And then we have something called the mid-Pleistocene transition. If this transition is when the planet went from this 40,000 years dominated world to another one called 100,000 dominated world. So this is when the eccentricity actually start to be more important than the obliquity in terms of modifying the climate of the planet, as you can see in this isotopic curve. Um, However, if we zoom this curve and we focus in some parts of them, for example, in the last 50,000 years, we have something called millennial climate variability. These are quick changes in the temperature of the planet that we can see in this curve. And if we zoom it, we will observe different changes that are called Danskar-Oskar events, and that those Danskar-Oskar events are composed by two phases. One is called the Greenland stadials, and the other one is the Greenland interstadials. And this is what we can observe in this black curve that shows the isotopes measuring the Greenland ice core. This is high resolution data set. We can see how this zigzag um, 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 dynamics are occurring in the curve. And basically what we observe is that the cool periods called Greenland interstadials produce a decrease in the isotope record, and then we have the Greenland interstadials that are these red colors, red letters on the plot, produce warmer conditions and reductions in the and increases in the Greenland isotopes. Why it's important to know this is because this millennial variability modifies the hydroclimate of the tropical area. So this is what I want to show you using this record. This record from calcium versus titanium iron is coming from Lake Petenitsa that is located here. This is the record that I'm going to explain to you later as well in the last part of the presentation. And this record is also from my PhD. And what I'm showing you are this variability in this ratio that is used as an indicator of evaporation on the lake. So basically, what we can see is that when we have these Greenland stadials, so the cold periods, we have an increase in the evaporation, and when we have these Greenland stadials or the wet environments, is when sorry, the warm periods is when we have a wet environment in Lake Petenitsa. And this is related with the tropical convergence zone in this area in the tropics because, well, you might know that the tropical convergence zone is this low pressure atmospheric region where we have high precipitation and is migrating annually. In the summer of the north hemisphere is positioned more in the north, and during the winter is of the north hemisphere is positioned more in the south. So this has not been constant through the time. We know that during these Greenland stadials, interstadials, IPCC have has had some changes. So this is what we observe in Lake Petenitsa. So as you see in this animation, during the Greenland stadials, we have that intertropical convergence zones migrate to the south, and then producing evaporation in Lake Petenitsa, and then during the interstadials, we have that the IPCC migrates to the north, and then Petenitsa became wetter and with less evaporation. No, so this has been occurring during the last 50,000 years, and that's what has produced this millennial cyclicity. However, also we have something called Heinrich stadias or Heinrich events during the during the coldest Greenland stadias, and this is basically when the ice sheets in the North Atlantic migrate to the south and producing a high deposit or deposition of what is called iceberg raft debris in the North Atlantic. And this input of cold water produced the collapse of the Atlantic meridional overturning circulation. That is basically one of the responsibles of the heat transportation and moisture to the Central American region. And that's why we have a reduction, a considerable reduction in the precipitation in Petenitsa, and we have these evaporitic deposits in the lake, as you can see in the photo. And basically, what we reconstruct is that the lake became shallower and with high evaporation rates during the Heinrich stadials. So this is what have occurred in the last 50,000 years. It's really known in the paleoclimatology of the area, but there is something that we have observed recently that is also millennial climate variability during interglacials, during the maximum of the interglacial, and this is something new, is because it's like hardly detected, and in the tropics. This is what I'm showing you in this plot. So I'm not gonna explain to you the big figure that you have to the uh, left, right, left to the left exactly. But I'm gonna focus only in these three plots or four plots that you have to the right. So the tropicality index, this curve is based on pollen that likes a warm environment. So this increases, indicates warm conditions. This is the titanium curve from Lake Petenitsa as well. This lake in Guatemala that I was explaining to you before. And you can see the decreases in the titanium, and this is a proxy for runoff and precipitation. So low values of titanium indicates low precipitation. And these are matching as well with other records in the region, like Lake Chalco, that is located in central Mexico, close to Mexico City. And you see that these decreases in titanium in Petenitsa in Guatemala is also occurring in Lake Chalco, and these reductions are also matching in some cases, not in all, but in some cases, with increases of these colitophorids in the North Atlantic in this record in the ODP 984, and this is an indicator of cold water input to the North Atlantic. So apparently there is a millennial scale variability as well in the MIS5 in the interglacial, but something that is strange because we will expect to have humid conditions during all the interglacial, but we have this this cyclicity. So the question here is what is producing this millennial variability in the interglacial? So because we don't have, it's a warm period, we don't have these ice sheets in the North Atlantic, as for example, during the transition to the glacial periods, as I showed you in the Greenland stadials, interstadial, so what is producing that? And in 1993 or in the 90s, some researchers investigate this record in the West Africa, in the tropical, in the equatorial, actually, in the equatorial region. These fixed records are different percentages of this coccolithophorid, Florifariaceae profunda. Sorry for my pronunciation. I'm geologist. But and they did some frequency analysis to detect the signals, and these are the results that they obtained for each of those curves. These peaks that you can see around 7.8 kiloyears or 7,000 years are the frequency that dominate the record. So you can see that some of all of them are around between 7 and 10,000 years, and that's what they call by that time. Um, eh, Cycles of half precession, no? But now we know that they are actually half precessional cycles. So with this, I would like to put the question like, could be these cycles that are mainly from the tropics, the responsibles of this millennial variability during the interglacial symphysis or not? No. So for for that, I would like to start with the second part of the presentation, that is this record from West Africa, um, and talk about what we have found in this record about in terms of high precessional cycles. But let me explain to you before what is a high precessional cycle. So in the equatorial region, we have the two times cross of the sun perpendicular to the surface of the planet, no? Because, well, the translation, the orbital changes of the planet through the year, no? So during the transition from winter to spring, no, we have a maximum in the insolation. This is the equatorial insolation values through the year. Uh, this peak occurs between winter and spring because the sun is perpendicular to the surface, so the insolation is perpendicular. Then during the summer of the North Hemisphere, you will have a reduction in the equatorial insolation because most of the insolation is focused in the North Hemisphere. Then during the in transition from summer to autumn, we have a second peak. This is because this insolation is mainly in the southern hemisphere. And finally, during the winter, the insolation again decreases because now we have a maximum insolation in the southern hemisphere. So this is what is com producing two peaks annually of insolation in the tropical region. If we transport that or translate that into the last 1.2 million years of the planet, we will see that these peaks doesn't occur constantly through time. We observe that sometimes they are more, the amplitude of the insolation change is bigger than in other times. So, for example, this blue curve here that I'm showing you is the spring insolation through time, and you see this, for example, high amplitude insolation changes, and then we have around 400,000 years this reduction in the insolation. But if we observe the autumn insolation through time, you will see that they are not matching. So they are actually intercalating each other. And if we zoom it in one part of the record, we will see that the time that occurs between one peak and the other one is around 11,000 years. And this match with the frequencies that we observe in the equatorial region with proxies. So that means that this inter in, in sorry these intercalations between these two insolation peaks are producing the high precessional cycles in the tropic. Uh, we observe that this is modulated by the eccentricity of the planet. So I mean, when the orbit is more closer to a elliptic shape than a circle, no, and yeah, so that's the basic of the high precessional cyclicity. But now we have several questions, like for example, what effect have in the West African monsoon? Because we know that in the past these high precessional cycles could modify other monsoon systems, like in the Asian monsoon. Um, what occurred with the West African monsoon, that is one of the biggest ones in the planet, no? And if they can have been keen in the evolution of the mid-Pleistocene transition, because actually there are still some questions about what could produce the mid-Pleistocene transition, why the, 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 the climate system was reacting more to the 100,000 years planet and not to the obliquity planet, no? Or if actually they are the presence of these high precessional cyclicities are a result of the mid-Pleistocene transition or not. So, um, or if this high precessional cyclicity is also connected to the millennial variability in the North Atlantic, so with the Greenland stadials, with the Greenland interstadials, if they are connected somehow, or if they are independent each other. And finally, if this signal that we observe in West Africa, in the West African monsoon, can be translated or transmitted to other regions, particularly to the Caribbean, and how. So these are some of the questions that this project is like, working on. And let me talk to you about this site, the site ODP 663. This site was really in 1993 by the by that time called Oceanic Drilling Program. Now it's called IODP COOP. And this record is really sensitive to do different modes in terms of the monsoon. So during the summer, the boreal summer, we have that the ITCC, the tropical convergence zone, is more positioned in the northern, and then the West African monsoon is more intense because the transport of the humidity from the sea to the ocean to the land. And then during the boreal winter, we have the ITCC migration south, and then the northeastern trades are coming from the Sahara, transporting dust and to the region to the site. No, so it's very sensitive to these such seasonal changes. Uh, we were measuring this core. This is approximately 39 meters length core. We made some XRF measurements, XRF fluorescence, every centimeter. So we have a really high resolution record of elements like titanium, calcium, iron. And this is my colleague Arne Ulfers, who started the measurements in 2022. And I'm following that work now. And these are the results of this high resolution measuring. They are two curves. One is the barium, the other one is a proportion of aluminum versus lithium, potassium, titanium, and iron. The first one is an proxy for primary productivity. It has been shown that is an indicator of how the primary productivity changed through time. And basically, what we observe is that the productivity change between the glacial and between the interglacial period. No, the interglacial is the red part with these red shadows, and the glacial period is the blue colors without a shade. And then this radio, the aluminum versus silicium, potassium, titanium, iron is an indicator for the West African monsoon intensity. So higher values indicate, or these blue colors indicate a higher runoff from the continent, and lower values indicate a lower runoff. So we can discuss this during the question session if you have a question about the proxy. But yeah, basically that is what we are reconstructing using these two proxies. But I'm gonna focus now only in the proxy for the West African monsoon intensity through the last 1.2 million years approximately. So what we observe is that basically during the interglacials or during the warm periods, we have that the West African monsoon was more intense, particularly in the last 800,000 years, when the monsoon can be really clear. You know, the increases in the runoff can be really, really clear. At the beginning, the amplitude of change of the West African monsoon is like not really clear. So we can see that some interglacials have the signal, but not all of them. And actually, there are some um, glacials that contain the signal, but actually, yeah, it's not really clear the signal. So, but after during the mid-Pleistocene transition, the signal it became clear. Um, and around 400,000 years during the MIS 11, so the MIS is basically an interglacial, the marine isotope stage. And we have this peak, the wettest period of the record. And something interesting is that in the American tropics, in Lake Pequensa in Guatemala, or Lake Siquin in Colombia, or Lake Chalco in central Mexico, all of them start the sedimentation, lacustrine sedimentation around this time. They are influenced by several geological processes as well, like volcanic eruptions or the erosion of the basin and stuff. But basically, something interesting is that around this age, when we have the wettest period, is when all these lakes start sedimentation. And after that, we observe that the amplitude of change in the West African monsoon start to be like more, like marked. You can really see that the interglacials are wet and the glaciers are dry. Then, if we compare our record with other records around Africa, we will see that well, we have this transect of north to south. So we have Lake Malawi here in the south, then we have our record, then we have this record of gamma radiation in Lake Bonswinti. We have the record of dust flux in this 659, and this record from the Mediterranean in the site 967. All of them are indicator of the monsoon system, um, and they are standardized. So values, well, except for my record, but all of the rest are standardized. So values above zero are indicators of wet conditions, and below are indicators of or dry conditions. So what we see is like three different parts of the record. So these blue colors in the map is only for like illustrative purposes. So that doesn't mean that the extension was actually like in that point, but only for outreach, let's say. What we observe is that my record, for example, and the record of Lake Malawi, that are the ones that are like in the southern part, doesn't really show wet environments, so they are actually more dry than the other ones, in the north. So that means that probably the wetness in the region was more focalized in the northern part of Africa than the southern part. And the signal of the monsoon, sorry, in the because of this uh, wetness in the north, the southern record doesn't reflect as well as in the north the monsoon variability. Then in the middle part, we observe a zone of transition during the mid-Pleistocene transition. No, we observe some wet periods, not all of them, but we start to observe them. And also in the southern part in Malawi, they start to see these wet periods. No, and in the north, basically, we don't observe that. We have these dry environments, and you can see this in the index of the 957. So that means that the wetness was more focalized in the central part of Africa, in the tropical part. And finally, in the youngest part, in the last half million years, basically, we observe like a matching in all of the records. So the records in the north still are more humid than my record, but they are reacting at the same way during the glacial and the interglacial. So that means that the monsoon system behaves as today since the last half million years. Then talking about the high precessional cycles, I don't know how many time I have. I had 10 minutes more. Oh God. We made this filter. This is an spectral analysis. So basically, what this curve do is this green curve that you observe in the record extracts the signal of the high precessional cycle. So we delete the frequencies that are not related with the high precessionals, and we leave only the ones that are related with the high precessional cycle. So when we see the higher amplitude in the curve, that means that the high precessional cycles are there. And when we have low amplitude, that means that the high precessionals are not there or are not recorded at all. So what I want to tell you, like quickly to start with the second part of the presentation, because I have only 10 minutes, is that there are some differences between the barium and the radio. I was expecting to have the same response, but actually we are talking about two different processes. So the barium is something happening in the water column, the primary productivity, and the other one is more related with atmospheric processes, like the West African monsoon dynamics. So, but they are presenting different, are sensitive differentially because they are representing different processes. So, in terms of the West African monsoon, uh, the high precessional cycles are only during some of them in the interglacials are, and most dominantly during the 104,000, 100,000 world. No, so that means that for having high precision cycles, you need a stable climate. So during the mid-Pleistocene transition, maybe the climate was so unstable that they could not be established at that time. No, talking about the relationships with the North Atlantic dynamics, so with the Greenland tiles, interstials, these are data, these blue bars are the number of events, of millennial climate events every 10,000 years. This is a record from David Hodel from 2 years ago. And we, our hypothesis was that when we have more North Atlantic events or millennial variability in the North Atlantic, we will have more high precessional cycles. But actually, that doesn't happen. They are like opposite each other. For example, in this part, in the MIH17, we have low millennial variability, so one peak here, but actually, it's like if you compare it with this amount of events, we don't see a matching, no? So this is something that is still under discussion. We are discussing it with my colleagues, but that means that the hypertensional cycles are something separated from the what happens in the North Atlantic. And if you remember what I told you in Central America, no, this millennial variability during the interglacial, so probably they are more related what with the high precessional cycle that what we have what is happening in the North Atlantic. So the tropical area of America is reacting to two processes, different processes, and that is something interesting. And the eccentricity basically doesn't seem to be like really. So the theory says and the model says that the eccentricity should be modulated in the presence of the high precessional cycles, but actually we see that that doesn't happen always. And we are trying to figure out, and now it's under discussion as well. So why is happening that? One of the theories, well, of or ideas or hypotheses is that the AMOC, the oceanic circulation, it can be modulating also the presence of the high precessional cycles or not. This is what I show you with this orange curve. But we are still discussing that. Apparently, in some cases, yes. For example, the MIS5, when the circulation is like more intense, is when we have as well more high precessional cycles in the West African monsoon, but not all of them, you know. So this is something uh, under discussion, and I hope to have a response uh, later. I'm going to skip this slide quickly because I have already mentioned it, the connection with of a record with the Central American records. So I would like to go quickly to the part 3 of the presentation in the last 5 minutes that I have. Sorry for that. But this is a record of Central America, so we will go now to Northern Central America, like particularly Lake Pichincha again. Um, this is the plot that I showed you before. This is the isotopes, oxygen isotopes in the last 300,000 years. And I'm going to focus only in the last 21,000 years. So as you can see, it's like only the last page of the history of the tropics, so compared with the 1.2 million years that I have explained to you before. And this period is interesting because if we see the models, we have 7 Celsius degrees change in the temperature of the planet from the last glacial maximum around 20,000 years ago to the present, to the pre-industrial levels. This is what is called the last glacial maximum, the deglaciation, followed by the Holocene, that is this stable climate scenario. And parallelly to this increase to these 7 Celsius degrees in temperature, we have again also an increase in the CO2 content in the atmosphere. So this record is from the record from Antarctica, sorry. We have an increase of 90 ppm since the last glacial maximum. So remember this data because I'm going to explain to you that later. 7 Celsius degrees with 90 ppms. No, so right now we have I'm trying to remember like also like 100 ppms more than the pre-industrial levels, but we have already 2 Celsius degrees. So let's think about that. No, if we see the models, the temperature that is reconstructed for the last glacial maximum, this is the mean annual air temperature is for the tropical area is around 2 Celsius degrees based on the models. But if we observe the data, the proxy data reconstructed from several records like Lake Chalco or Lake Tanganyika or Malawi or Clearwater Cave, They are reconstructing around 4 Celsius degrees, a decrease in the temperature of 4 Celsius degrees, no, compared with the 7, the global decrease, and what is recorded with the models, no, that is around 2 Celsius degrees. Also, if we observe the records, they have what it seems to be millennial variability during the deglaciation, no, these changes. Uh, but not all of them, you see. Like for example, this record in Indonesia is not have no Indonesia in the sorry in the East Africa, no East Africa, no sorry, East Asia, and doesn't seems to have it, no. But records like Tanganyika and Chalco, they seems to have it. So it seems that there is something happening that the records to the east doesn't have the millennial variability, but the records to the west have it, no. So to fill this gap, we need another record in the middle, which is Lake Petenitsa. So this is the lake, a photo during the drilling campaign in 2006. This is one of the biggest lakes in the lowlands in South America, and one of the biggest and the deepest as well. So the ICDP drilled the lake in 2006, obtaining a sequence of approximately 100, I forgot the name, the numbers right now. Wait a second. Um, but these are the numbers of the lake. So the lake is approximately 114 square kilometers. That will be equivalent to 16 Olympic stadiums. Have a depth of 165 meters. That is around approximately 3.5 Roman Coliseum, and a temperature of 25.5 Celsius degrees annually. This is the shape of the lake. It's elongated, the deepest part in the northern basin. You can see that the water depth, the temperature change around 40 meters depth, as you can see here, and the dissolved oxygen of the lake is also changing around 40 meters depth. So as I told you, was drilled in 2006. This is a photo of the lake from the north to the south. You have here the site where ICP drilled. This is La Flores city to the in the eastern part, and you have this Maya settlement in the northern basin. No, so we are observing from north to south. So this is the northern part. Yeah, we know the temperature change based on other proxies, like for example, pollen calibration curves. We know isotopes, Crumpet isotope thermometry based on Ostracods and gypsum, and as you can see for the deglaciation, they are super different. So pollen is indicated and decreasing the temperature of around 3 degrees, but the clumped isotopes is saying 10 degrees Celsius. So there is like a mess in the reconstruction because these proxies are sense the sensitivity of these proxies is different, no? So we need a new approach to reconstruct the temperature to confirm that, or not to confirm, but to have another data that validates the change of the temperature in the region. And for do that, we are using these biomarkers. This is the glycerol glycerol tetraters, or GDTs for friends. And these molecules are produced by different archaea in the bacteria living on the lake, and these molecules are basically protection for these organisms. Um, so our goal is to reconstruct this temperature using this proxy and also other limnological properties. This is some photos. These are some photos and videos during the processing of the samples. You can see there in the laboratory, taking the tracks, processing it, and these are basically the data that I'm gonna share to you today. This is something called humidity index. This is an indicator for precipitation. We have the total organic carbon as an indicator for the organic matter content. We have the portion of total organic carbon versus total nitrogen for the organic matter source. We have dissolved oxygen. We have the reconstruction of the mean air annual temperature finally. So I would like to go in 3 parts. First, the last glacial maximum, then the deglaciation, and finally the Holocene with the Maya period, where it's when we have this human activity around the lake. So the first part is the last glacial maximum. this animation help a little bit to understand what is happening. And we reconstruct some moderate humid environment with rich in organic matter. We have the sources that are mixed from the algae living on the lake and also from the vegetation surrounding the lake. We have an dissolved oxygen that is super high, around 6 milligrams per liter. Sorry, and yeah, the temperature is around 20 degrees Celsius. That is approximately 4 Celsius degrees less than today. That makes sense, and that match with other records in the tropics. So that's important. Then we have the deglaciation, and this is when we have a mess because we have these Heinrich stadials, we have the something called the younger dryas, and as you might remember at the beginning of the talk, these stadials are characterized by because the intertropical convergence zone was in the south, so the lake was super dry. We have these evaporitic deposits, on the bottom of the lake, and that's why we think that the communities, the bacteria communities, were changing a lot. Because when we reconstruct the temperature of these cold periods, actually we have temperatures that are 10 Celsius degrees lower than today. Um, this is unrealistic because it's not possible that we have during the Heinrich stadial that was less cold than the last glacial maximum. We cannot have 10 Celsius degrees, no. So we are suggesting that it's because this change in the bacteria community, because this extreme dry period that basically modify the bacterial composition of the lake. And that's why we cannot rely on these temperature changes, sadly. And finally, during the Holocene, something important that happens is that the humans were there around 3,000 years ago. We can see that in the increase in the total organic carbon versus total nitrogen indicator, indicating a high input of terrestrial organic matter. Um, the oxygen became less because if you are putting more organic matter on the lake, the oxygen that is at the bottom is being consumed. The temperature doesn't seem to change a lot during the last 10,000 years. It's basically super close to the mean annual air temperature, the current one. And yeah, we can. It's super nice that we can observe this on the lake because or this increase in the total organic carbon, total nitrogen is matching with the fierce populations on the lake basin. So this archaeological settlement in the northern part of the lake. This is another core. It's not the same one that talking to you. This is from my colleague Jonathan Obrist, and he drilled that part of the Tenisca, and he obtained these curves. So we have the titanium and the charcoal. The charcoal is an indicator of fires. So what we can see is this change in the stratigraphy having laminated, no, sediments. Then we have this massive deposit associated with the titanium and with the increase in the titanium. But before that deposit, we have an increase in the charcoal particle. So what he's proposing is that the people arrive to the zone, to this archaeological site, and they start to fire to exactly to burn all the vegetation surrounding the lake, and that's why we have this increase in the fires in order to construct the streets and to start to build houses and stuff. And that's what we observe here. The soil signature is when they start to to expand the peninsula for constructing more houses, and finally uh, in at the end of this massive strata around in the year 300 is when people leave. They abandon the area, and the ecosystem could recover again as is today. And it's interesting that by the same time that he's registering this, we are having this increase in the top TN, even we are approximately 2 kilometers far away from the archaeological site. So it's super interesting. And yeah, I'm gonna skip this because I think we are already done with the time. But basically, what I would like to show you is that Lake Botany is an important record for understanding the tropical sensitivity to changes in the temperature. And it's important because, as I told you, in the last 24,000 years, we have an increase of 90 ppm related with 4 Celsius degrees in the area. and that has produced a change of 40 meters water increase based on the biomarkers. And if we observe in the last 45 years, we have already the same amount of ppms related with an increase of 2 Celsius degrees, and we will expect that that will produce as well future water level increases because we observe it on the past, no? And it's important because there are people living there. There is a city there next to the lake. And what could happen if we see that basically in the last 20 years, the lake level has increased, uh, change annually, but actually in a long-term scale, the lake is becoming deeper and deeper, and what is going to happen with all these people, in the future. So that's important, and that's why it's important to know what happened before to understand and make projections about the future. And with that, I would like to thank you too much for hearing. I'm sorry for taking more time than was expected. I never measured that. And I would like to thank you to the organizers of this talk, and to all my colleagues for doing this work possible. And yeah, I'm open for questions.
Great. Thank you so much for that awesome talk, Rodrigo. Um, yeah, super interesting stuff. Yeah, so just a reminder to the people in the audience, you can send your questions directly to the questions at PaleoPerks host. But we already have a couple questions that have come in during the talk. So if it's all right with you, Rodrigo, we can get right into the Q&A session.
Perfect. Go ahead.
So great. So I will post the question in the chat, and then I will also read it out loud. So the first question reads, do you think that these methods could be useful for understanding changes related to climate change in the future, perhaps with some sort of forward modeling?
For instance, change related to climate change in the future. Uh, so I don't know if I understand the question correctly, but the methods that I'm applying, if they are useful for what is going to happen in the future. Uh, I think that's the question.
I think
Uh,
so.
so I think so. I think so. I think that they have been already super useful for um, for what happened in the past, in not only in the last 1 million years, but also in the recent past, no, so in the last 100 years, for example. So I would say yes, that's the base of the paleoclimatology, no?
Mhm.
I don't know if I replied the question, but
Yeah, I think that you got the gist of it. So thank you. Looks like there's another question that was just posted in the chat. Um, and this question reads, why is increased humidity reported during the LGM if conditions are generally considered to be dry in the Pitan Itza? What could be driving this increase?
yeah, that's an interesting question that I'm working right now. So, yeah, well, actually, in Petenitsa, the environment was moderate. That's something that I'm discussing in this project. So, in Petenitsa, it's well known that was moderated wet, no, was not as dry as was expected. This is what we know with some other data. What I'm observing are punctual dry episodes on the lake. So the biomarkers are saying high dissolved oxygen, but they are like how to say this, like not during all the period, but some uh, particular events that occur. And then in terms of all the regional reconstruction, it's well known that the last glacial maximum produced drought in the tropics, and particularly in the tropics of America. But what we are observing in a research that I'm doing now is that the signal is super regionalized. Like the different regions have different responses to the humidity change during the last glacial maximum because other factors, local factors like the orography, for example, could promote these changes. So not everything became dry during the last glacial maximum. Mhm. Yeah.
Great. Thank you for that response. Yeah, hopefully that answered the question. But I think so. It was very thorough. Okay, I will move on to the next question here. Okay, perhaps more of a general question. How variable are the various ODP sites between each other? Are sites globally relatively consistent?
Mm, that's an interesting question, and I don't think so. I don't think so. It's because depending on the position of the course, you are having different signals. So, as I told you, this question is under discussion. But for example, the Mediterranean records are more north than my record, so not necessarily they have to be coupled. Like what is reflecting in the Mediterranean maybe is opposite to what I should expect. No. Also, for example, the Mediterranean record is more influenced by a fluvial input, like the Nile River, no? So e- e- all the every change that the Nile records because changes in the monsoon, the record in the Mediterranean will have it, no? My record is a little bit more far away from the coast, so it's actually sensitive to big changes. So it's not as sensitive as the record in the Mediterranean. But even though I will expect that these orbital big changes will be registered. Um, yeah, exactly. Yeah, so depends on the position of the latitude of depends of the closeness to the shore. It's gonna be the signal. So, yeah, but it's under discussion everything. So, but thank you for the question.
Okay, great. Thank you so much. We're down to our last question. So unless anyone else in the audience has any questions they want to ask, this will be the last one. So if you have something, then send them now. Um, but for now, here's our last question, which I think is referring to maybe some of the photos you discussed early in the presentation. What causes the sediment cores to be the different colors during glacial and interglacial periods? I suppose it refers rather to like what is actually the giving it the color.
Yeah, yeah. Well, if you are referring to the first photo that I put in the presentation in the Marine Corps, is more related to the organic matter content. Usually, the dark color is going to be related to the organic matter, m- more richer organic content, and the whiteness is because you have more carbonate, no more like organisms like foraminifera carbonate organisms living there. Now, if you are talking about, for example, the photos in the lake, like these laminated records, or um, depends on the composition of the sediment, obviously, no? So the laminated usually will indicate that the lake was deep and good stratified, no? And but if, for example, if suddenly you have an input of organic matter, I don't know, because this human activity that I showed you before, no? Then you have darkness sediment. So the color can be an indicator, but then you need to go inside the sediment to see what is actually giving the color. Yeah. Thank you for the question.
Uh, Great. Yeah, thank you for your answer. I think then that's going to be the last of our questions. I suppose if anyone in the audience has any pressing questions that they think of afterwards, maybe they can reach out to you directly. I hope, yeah, I don't want to speak for you, but yeah, thank you
Yeah.
for the great presentation and the great Q&A session.
Thank you so much. And also, if somebody has more ideas or more things to discuss with based on my data, I'm also super open to hear them. So please go ahead and let's to discuss it. Yeah.
Great. Yeah, we always love good scientific collaboration and any
Mhm.
opportunity for that.
Yeah.
Great. Well, yeah, thanks again. I will then do some final closing announcements here. You all can see my screen, correct? Does that? Hope so. Okay. Well, yeah, thank you all for joining us. Again, we ask that you please fill out the weekly feedback form so that we can learn a bit more about today's seminar. Additionally, we are always eager to have outstanding early career researchers nominated for the seminar series. So please, please, please feel free to nominate some of your early career colleagues either through the link or through our website. We would really encourage you to do that. Our next seminar will be happening next week on February, and we'll be hearing about geochemical reconstruction of climate from Jonathan Stein. So thank you all for attending, and we hope to see you then. But for now, as mentioned, Rodrigo said that he'd be up to stick around for tea time, which is just an informal conversation about the talk in a very relaxed setting for 10 or 20 minutes. So if anyone is interested in that, we'd encourage you to stick around. But for now, we will have a quick 2-minute pause. So get up, get a drink of water, stretch your legs a bit, and we'll meet back here in 2 minutes and we'll go from there. So thank you everyone who attended, and thank you again, Rodrigo, for the awesome talk.
Thank you so much, and thank you so much everyone for being here. See you in 2 minutes.
Bye.